Let us look at diagonalization of a square matrix. Diagonal matrix is a square matrix whose off-diagonal elements are all 0. So something like this. The principal diagonal positions have some numbers and rest of all are zeros. Now a square matrix B is said to be similar to a square matrix A if there exists a non-singular matrix P such that P inverse AP is equal to B. So if P inverse AP equal to B, then B is similar to A. If B that we arrive at is a diagonal matrix, then A is said to be diagonalizable. So let's look at an example. Let's say A is equal to this matrix 2, 4, 0, 5, a 2 by 2 matrix. Remember the characteristic polynomial? Determinant of A minus lambda I is equal to 0. Let's write it in this form. Determinant of 2 minus lambda, 4, 0, 5 minus lambda equal to 0, and which implies 2 minus lambda times 5 minus lambda is equal to 0 because 4 times 0 is 0. So that means lambda equal to 2 or lambda equal to 5 are the eigenvalues. So now going back to this system of linear equations, let's substitute the first value of lambda, that is lambda equal to 2. We get 2 minus 2, 0, 4, 0, 5 minus 2 is 3. Reducing this matrix, we get R1 replaced with R1 by 4, R2 replaced with R2 minus 3R1. We get 0, 1, 0, 0. 0x times 1y equal to 0. That means y is equal to 0. X is a free variable. Let x equal to k. So x1 is equal to k 0. For k equal to 1, remember capital X sub 1 is the set of all solutions, whereas smaller x sub 1 is one of the solutions. 1, 0. Now let's take lambda equal to 5. So 2 minus 5 is minus 3, 4, 0. 5 minus 5 is 0. So here again, rank is 1. So we have minus 3x plus 4y equal to 0. That is x equal to 4y by 3. And y is a free variable. So let y equal to k. Then x equal to 4k by 3, y is equal to k. The set of solutions for eigenvalue 5 is 4k by 3 comma k. And a particular solution, let's say for k equal to 3, we get 4, 3 vector. Now using these eigenvectors x1 and x2, we build the matrix of vectors P equal to x1, x2. So we build a matrix where each column is one of the eigenvectors. So we have P is equal to 1, 0 for eigenvalue lambda equal to 2 and 4, 3 for eigenvalue 5. So we have arrived at P. What else do we require? Remember, we are talking of P inverse AP equal to B. So that means we have to figure out the inverse of P. We know the formula P inverse equal to 1 by determinant of P times the adjoint of P. P inverse is equal to 1 by determinant evaluation times the adjoint of P. Simplifying it, we get P inverse is equal to 1 by 3 times the adjoint. So now we have P inverse. So let us now find B, that is P inverse AP. So we have now the given matrix A, we have the matrix of eigenvectors, we have P inverse. Now, let's evaluate P inverse AP and we arrive at B is equal to 1 by 3 times 60015. If we take 1 by 3 inside the matrix, we get 2005. Now here if you notice, B is a diagonal matrix and P inverse AP is equal to B, which implies B is similar to A, which implies matrix A is diagonalizable. Now, let's verify whether this is correct or not. P inverse AP is equal to B, pre and post multiplying by P and P inverse respectively. We get this. Simplifying it, we get A is equal to PB P inverse. Now let's multiply PB P inverse. Once we multiply, we get A back 2405, 2405. So that was diagonalization of a square matrix. In the next session, we will look at a 3 by 3 example. That's it for now. Bye.